This is Antic, the Atari 8-bit podcast.
These guys at Motorola aren't going to do the microprocessor that we need to do, and that is a low-end microprocessor to compete with the Intel 4040, which sold for about $29. I had a bet with Rod Orgle, and Rod Orgle said the 6501 would outsell the 6502. I'm an empowerment technology. I want to empower people to do their idea. That's what I did for Chuck. That's why he came to me. Now, you'd think that I was a big fan of Apple, and I'm not. The reason why I'm not is they killed off the Apple II to make room for the Macintosh. All of those old brands, Apple II, Commodore, Atari, and the old Nintendo, could all come back to life with the right relationship. And we have the technology.
I'm Kevin Savitz, and this is an interview episode of Antic, the Atari 8-bit podcast. Bill Mensch is co-creator of the 6502 chip, the microprocessor that's the heart of the Atari 8-bit computers, the Apple II, the Commodore 64, and many other classic machines. This interview occurred August 6th, 2015. You can start by telling me, what's it take to develop a processor, and what did you have in mind when you developed the 6502?
Yeah, so what happens is a little bit of background, not trying to take up too much of your time in the interview process here, but actually, I'm a hardware guy, but actually I started out more or less in software. So I'm actually a software guy converted to a hardware guy, and the software that I did was at the University of Arizona. At the University of Arizona, for my senior year, my second year, because I only spent 2 years working on my BS, for my senior year, I supported myself with a half-time job working for a professor that came back from Princeton, and at Princeton, his sabbatical was working with the tokamak fusion project they were working on. And when he came back to the University of Arizona, he wanted to simulate the hardware that he was working on at Princeton. So he's a nuclear physicist professor, so I was taking a full load of engineering class so I could graduate in 2 years. Plus, I was taking 6 credit hours of graduate level nuclear physics, so that was required for my half-time minimum wage job simulating fusion. So that got me into the software world, and as a result, when I did get my first job at Motorola, I simulated everything. So that means that I simulated the integrated circuits so that I knew the transistor functions were working correctly. And when you put 2 or more transistors together with resistors, all of the equations for the transistor operation due to voltages and currents are all in the simulation of the transistor. So I was simulating the transistors so that I would know that when the chip came out, the chip would work. And so I also simulated the process that manufactured the transistors. So I knew everything about the way the physics of semiconductors worked with voltages and current and resistive characteristics. And so I built up my understanding through my software simulating everything about an integrated circuit. So once you do that, you realize that actually a microprocessor is a small computer. So a microcomputer is just a name for a small computer. And so if you're working, and as I was, the language that I programmed in was Fortran. And Fortran is still used by astrophysicists because it's the language that works most efficiently for formulas. That's what it's called. Formulas translation, I think, is what Fortran. Fortran was the first high-level language also. So now, that simulation led me to understanding that, like at the University of Arizona, working for this nuclear physicist professor for fusion, he wanted me to get my PhD in nuclear physics, and when I asked him, and also back up a minute, I took over a PhD dissertation. So this guy graduated with a PhD in nuclear physics, and so nobody else was available in electrical engineering, which is what he wanted. So I was the only available student that filled the criteria that he was looking for, and nobody else really wanted to work and take all this extra effort. But this was a choice that I made because of the situation I was going through. And so as a result then, I would simulate this fusion and the fusion simulation, and I had the computer for 2 hours in the middle of the night, let's say from 2 o'clock in the morning to 4 o'clock in the morning. And so when I asked the professor, and that's because it cost $300 an hour for the entire computer facility, using every peripheral, every bit of the power. No other program could run when I was running that computer. So essentially, I had a personal computer at the University of Arizona in 1970-71. Now, how many times would you have to go to a computer building with a card deck in the middle of the night before you'd say, well, you know what? If I had my own computer, I could do this 24/7, but the other thing is I wouldn't have to get up in the middle of the night. And so that's just some basic thinking you go through. So what happened was I asked them how soon they were going to harness fusion energy as an energy source, and he said their goal was by the year 2025, which is in about 10 years. And I said, well, wait a minute, that takes longer than it takes to build a house. That's a long time. Wow. So let's see, 1970, 2025, it looks like about 55 years. And so I said, well, no, I really want to get a job, so I'm not going to take you up on your offer for me to get a PhD here. So that's when I realized that having your own computer would probably benefit, because not only benefit the person having an own computer, but maybe we could collapse the 55 years down to maybe something more reasonable like 20 years. So that was my thinking. So in 1973, after having designed not only a computer chip for Olivetti at Motorola and the 6800 and the peripherals, in the middle of the design of the PIA, which is an I/O chip, I suggested to Chuck Peddle that we could do a home computer, and this would have been around December of 1973. So I wasn't planning to do a home computer. I was suggesting a home computer would be what you could do when you combine a microprocessor with I/O and memory, both data memory and program memory, which was about the same time that the Hewlett-Packard 35 or 45 or whatever the number was, having a fixed function of mathematical functions like add, subtract, multiply, divide, and square root, and some other things that the HP calculator did. So all I was doing is saying a general purpose microprocessor with general purpose I/O and the ability to load programs in it would be that personal, or I didn't call it personal, that home computer that accountants could use. At the same time, I happened to be installing sprinkler systems in Arizona. If you don't sprinkle the grass, it dies. So you need sprinkler systems. So that sprinkler system, each one of the valves was costing $60 or something like that. So if you just said you had a few valves and you had a controller, pretty soon you'd say I could replace everything but the valves with a home computer. And so that's what I was thinking in 1973, because I had patents on all of the integrated circuits associated with the 6800. So Chuck came to me and said, Bill, do you want to go to Austin, Texas? That's where they're going to move us. I said, no, I've driven through Texas a few times, coming back and forth from Pennsylvania to Arizona, and the only thing good about Texas is leaving Texas. So for me to stay in the heart of Texas, with Austin, Texas, is where they moved the microprocessor group to, I said I'd rather have a different choice. And so Chuck came to me because he knew I knew the whole thing, and I knew the process, I knew all the semiconductor engineering of it, and as a result, having proven myself and working with him on the PIA and the microprocessor. And so he said, well, how about if we build a team to design a microprocessor, and we'll figure out where it is, because these guys at Motorola aren't going to do the microprocessor that we need to do, and that is a low-end microprocessor to compete with the Intel 4040, which sold for about $29. I said, right, that's the place to go, because that's going to be embedded in everything that needs microprocessor. So what happens is, he comes to me, we meet with a guy named Paul Barossa, who was the head of central research at Motorola, thinking that Paul Barossa would help us figure out how to start a company or find a company that wanted to acquire a team that wants to do a great microprocessor. Now, I had already designed 2 microprocessors, and I, at that point, understood what it took to build a microprocessor with an advanced manufacturing process called depletion mode loads, NMOS, N-channel MOS technology. Motorola didn't have such a process. Intel didn't have such a process, but as the semiconductor engineer, we knew that depletion loads were going to be better than the enhancement mode loads that we had to deal with. And we were the only company, Motorola was the only company, to do a 5-volt only microprocessor. Intel had plus 12, minus 12, and 5 volts. So that's 3 power supplies to do a microprocessor. Motorola had a single 5-volt supply on the 6800. And as a result, the technology to build a 5-volt only microprocessor using enhancement only devices requires a lot more transistors and a lot more complications, but we got all of our circuits to work. We knew how to do it, but I knew that the depletion load process would be the best process for the microprocessor technology. Now, how did I know that? I was in control. I designed the microprocessor. All the microprocessors were built on the same manufacturing line. I designed the manufacturing control monitor that was stepped into every wafer of the 6800, and I don't know when they retired my process control monitor, but I had both enhancement devices for loads and also depletion in the same orientation on that monitor. All they had to do was implant it, and Motorola could have had the process that we had at MOS Technology. They did not want to do that until basically I was walking out the door. So when I got to MOS Technology, I said, that's the process we need. We get that process. We have less transistors. It'll be higher speed. It'll be lower power. Everything will work better. And that's what they developed. So in 1 year, we created a brand new process that Motorola and Intel did not have. They did not have at MOS Technology. Theirs was all PMOS. So we're working with NMOS and depletion loads. And when the chip came out, Rod Orgle was a logistics. He was a logic engineer, but he also knew semiconductors. So when Chuck came to me to build a team, I said, I need Rod Orgle. I want Ray Hurt to do the process control monitor. I went to school, Ray and I went to school at the University of Arizona. I actually hired my study partner when I went to interview students at the U of A for Motorola. After 1 year on the job, they sent me to U of A to interview students. Then after I interviewed the students, gave them the results of my interviews, they came back to me and said, we need one more engineer out of U of A. Do you know somebody? I said, yeah, my study partner, he's studying on his MBA right now. I'll ask him if he wants to work here. He got the job. We worked together. So what happens is, so I say to Jack, we need Rod Orgle, we need Ray Hurt, we need Mike Janes, and we need Harry Bauckham, and that's the semiconductor team that made the 6502 happen. Mike Janes and Harry Bauckham were mask designers. We got one more mask designer after appearing at MOS Technology, and then Chuck got the production manager from MOS. His name is Terry Holt, and then he also brought with him an applications engineer from Motorola. His name is Will Mathis. Will Mathis, Rod Orgle, myself, and Chuck Peddle are the four inventors of the 6502 microprocessor. However, I'm the one that designed the decimal correct circuitry that's what we had patented. Now, going back to something, Chuck is a systems guy. Chuck understood a small system requirement. Chuck built the first point-of-sale terminal for Singer, I think, back in New Jersey. So he knew small systems, but Chuck worked at General Electric's mainframe computer facility in Phoenix, and that's how the connection between MOS Technology and the Motorola team was. John Pavinin was also at the GE mainframe, and he started MOS Technology with two other guys, Don McLaughlin and Mort Jaffe. So now the connection was that John Pavinin knew Chuck Peddle and knew what was going on back in the GE days, and so that's how we got connected. And so then I headed up the semiconductor engineering of the 6502. Now, there's more to be talked about 6502. The Atari uses 6507 in the Atari games, and the 6532. Ray Hurt was the project engineer of the 6532, but I had already designed the 6530 chip that was used in the Kim system. So Ray Hurt and I have a patent on the 6532, and the combination of the 6507 and the 6532 were the core of the Atari game system. The 65,
VCS, the Atari 2600 game system.
Yeah.
I mean. Okay.
Yeah, and so then there's another microprocessor. I don't know if it's which number that Atari used, if it was 6502 or not, in the Atari computer, the 600 or the whatever it was, 800. But going back to that, the difference between the 6507 and the 6501, actually, the difference between the 6501 and the 6502 was about a dozen transistors that I suggested would be put on the 6501 to make it a 6502. The reason why I suggested that is Motorola in the 6800 and also with Intel in the 8080, they had a clock generator chip that had to meet the characteristics for a non-overlapping clock. Now, as a semiconductor engineer, and probably this is way out of your league of understanding, or at least...
We've been out of my league of understanding for quite a while, but keep going.
Well, so this is the truth. This is the facts. And so we'll get to the right level for where you're going. But you were asking me about the 6502, and most of this is not known, or if it's known, it's not known in a coherent way by those experienced in the semiconductor engineering world. Mm-hmm. So what happened was, Chuck is off on a marketing thing while we're designing the 6501. He comes back, and I said, well, how about if we just put the clock generator right on the chip? And he says, well, what's that going to mean? I said, well, it's really not going to mean anything from a manufacturing cost standpoint. The chip isn't going to be any difference in size. I can hide the transistors underneath the metal, and so it's not a bigger chip. There's nothing, it's not going to cost any more. I just put the clock generator on it. And the reason why is because an external clock, if it's manufactured on a different, which it would be, on a different process or a different wafer, that the characteristics of that clock generator are different. Like, for instance, it could be a slow clock generator with a fast chip, and as a result, these clocks are going to be overlapping, and it's going to cause problems. So Motorola was selling the $69 clock generator to go with this $375 6800. I said, well, throw the clock generator on it, and we'll make it a metal option. If you want it, great. If you don't want it, great. So that's the difference between the 6501 and the 6502. The reason why I have been, I had a bet with Rod Orgle, and Rod Orgle said the 6501 would outsell the 6502. And I said, well, why do you think that? He says, because of the marketing of Motorola. They're going to be selling it, and when they plug in a 6800 with our PIA, they're going to build it all around the 6800. We'll just take the 6800 out, plug in a 6501. We're good to go. All the sales and efforts by Motorola, we'll just cannibalize it. We'll get the business because we have a lot smaller, lower cost chip than the 6800. The user is going to go with us because we have a lower cost, much lower cost microprocessor. I said, okay, Rod, while we're waiting for the chips to be actually manufactured, it took about 2 weeks. I said, Rod, I'll bet you the 6502 outsells the 6501. He says, no way. There's no way. Who's going to be selling the 6502? I mean, okay, we have a few guys like Will Mathis and maybe Chuck going out and beating the bushes, but we don't have near the team that Motorola has selling a 6800. And if we have something plug compatible, they'll buy ours. I said, okay, Rod, the bet's on. I'll bet you. It could have been a six-pack. It could have just been a bet like you normally met. Gentleman's bet saying, I'll bet. So when Motorola sued us because we violated their patents, because we were actually doing things that I already had patents on. And so we had patents on these things. Motorola comes along and says you can't have a chip that plugs into the 6800 socket, so you have to stop selling the 6501. At that day, who wins the bet, right?
Right.
No way, Rod. You just lost your bet. And so that's how I became a 6502 engineer. And that's the story. That's my story, and I'm sticking to it, Kevin.
Nice. Were you surprised that it ended up being such a staple of all many of the home computers over the next few years?
No. We knew, Rod and I knew, because we designed two other microprocessors. Mm-hmm. We knew what Intel was doing. We knew what Motorola was doing, and really, there was nobody else that counted. You look at it. Rockwell has had their PPS-4 and PPS-8, but Rockwell ended up licensing ours because they knew at that point, they designed their own microprocessor. They knew which was the best microprocessor. Now, when you look at it, we knew what would be an awesome microprocessor. And most people do not know what I mean, because I'm the only one that's calling it an addressable register architecture. So the programmers that program Apples, Ataris, Commodores, and Nintendos, they really didn't know in a conversation why the 6502 was so powerful. And I don't think the world really knows it, although we have benchmarks on our website comparing the 6502 to the 65816 to the 68000 and to the 8086. You can go online and see those benchmarks. I did not write the benchmark. It's an instruction level benchmark.
All right,
that
so
means
so tell me what makes it so powerful.
Well, think about this is an 8-bit microprocessor, but it can compete very well with a 16-bit and actually very well with a 32-bit processor. But what makes it so powerful is that in one 8-bit quantity, you get an instruction. You don't need any other information. Like, for instance, increment the accumulator, increment the index registers. You can do that with one 8-bit quantity. You cannot do that with the ARM processor. You cannot do that with some of the other processors out there, the 8086. You can't do that. So what happens here is if you say everything you need is in one 8-bit quantity for 256 different instructions. So if you look at the opcode table of the 6502, you'll see there's a lot of not used opcodes. Mm-hmm. And the reason why some people call them is unusual operations or illegal opcodes.
Right.
the reason for illegal opcodes is we didn't care what the opcode did. We only care what the ones that we want it would do. So if you put in a non-defined opcode that some people have found, we never looked at it. I have never specifically looked at what all the other opcodes would do on the 6502, the original, because it wasn't part of the design. If the opcode that you want works, that's all that was required. So if somebody tested some of these other weird opcodes, you go, oh, so it increments both the index register and also the accumulator at the same time or whatever. Well, wow, that's interesting. We didn't know what it did because we didn't care about what it did.
So that's just pure luck of the design, what any illegal opcode would happen to do.
Oh, well, we never thought of them as illegal opcodes. They were called unused opcodes in the way we thought of it. Okay. So we weren't using those opcodes. So they weren't illegal. You can do whatever you want with them, but we weren't going to tell you what they did because we didn't even know, we didn't care what they did. Mm-hmm. So it's not illegal. You're just using it because you want to use it. And so those are fun facts. What does this other opcode do? But look at the 65C02. Because I knew people were curious about those things, guess what all the unused opcodes do? Do you know?
I have no idea.
They're no operation, so they don't affect any register. So that could have been disappointing to somebody that wanted to do something weird with an unused opcode. So I give you the cycle count for each of the unused opcodes in my datasheet. So now you can say, oh, I have a no-op that uses 2 cycles or whatever the no-op does. I think it's 2. No operation, 2 cycles later, you didn't do anything. Well, all of the unused opcodes now have different cycle counts. Some of them are common because of the way you decode the logic for the instructions. So actually, there are no unused opcodes on the 816. So the one opcode that I reserved for called WDM, that one is a no operation and is meant to be a segue to another set of opcodes that I never did.
Like a bank, like bank switching in, we're going to the second set of opcodes, that sort of thing?
Yeah, it would, well, yeah, like for instance, if you wanted to have a set of floating point, let's say you wanted to have floating point operations on the microprocessor, then I could go, the first byte would be WDM, the second byte would be the floating point operation.
Why did you never do them?
Because, think about it. If you add all these other things in it, what are you getting? A speed up, right? Mm-hmm. I already was doing what I wanted to do, and my microprocessor was outperforming the 68,000 and the 8086. But when you trip over that boundary to the 8086, look at what's in the 86 compared to the 816. Look what's in the 68,000 compared to the 816. And you'll see that what you're getting is a whole lot more complications. And that's why when my nephew worked for me to get his electrical engineering degree from ASU, both my nephews, Rod Orgle, who I was just talking to, he's a software engineer, and Andrew Hall worked for IBM, Intel, after he left my company. He worked with them in Chandler, and then he was moved to Portland, Oregon for designing the Pentium Pro microprocessor. And that Pentium Pro ran at 200 megahertz at the time. Andrew worked with about 500 other engineers. So when you trip over going from my 816 to something competitive, you need about 1,000 engineers. And so that's why I never did it. Now, did I specify it? Can you find a data sheet for the 65C 832? You can. Do we have a product named the 65C 832 PXB for a programmable accelerator board? We do. We have one of those. We sell those. So the thing is that when you go from the 816, you have to add about 500 engineers.
Wow.
And the reason why is because you have to compete with Intel, AMD, and at the time, IBM, MIPS. You have to go to the Spark, which came out of Stanford, I think. No, I don't know which one came out of Stanford. I think MIPS came out of Stanford, and SPARC came out of Berkeley or something like that. So you have the RISC processors, you have Cambridge behind the ARM processor, and when you do that, you have just elevated yourself to a whole new ecosystem, and I was happy with what I did with the 02 and the 816. So every time I look at a 32-bit processor, I end up with, why not recommend the ARM processor? Those guys came to me in 1983 to design the ARM for them, and I said, no, you're asking me to do something that's not compatible with the 02 and the 816. They wanted me to stop basically the 816 because the British Broadcasting Company, British Empire's Acorn, is where ARM came from. It was called Acorn RISC Machine. Then it was Advanced RISC Machine. Now it's just ARM because it was never really a RISC machine, but it followed the RISC concepts. And so therefore, ARM doesn't want to be known as a RISC processor, and it's because they really aren't. However, they have a lot of the characteristics. So now let's go back to something. If you go back to the they called it addressable register architecture, you understand we've had floating point library for 25 years, 30 years. A floating point operation is possible because of the way the 6502 instruction set works. So you can do a double precision floating point number in software. That's what we have. That's the floating point library. So if you want to add in a floating point processor like they did on the 486, when they went from the 386 to the 486, that's when I bought for $125,000. I switched over from my Calma GDS2 system to a network of Micron 486 processors because I knew once they put the floating point processor in there, then the software would use that. So all of my design tools would run on that processor. I switched from the Data General Eclipse to a network of, I think it was 15 or so Micron computers. We had to wait for the 486 to come off of the production facility before we could take delivery on, I think they were about $7,000 per node, per PC. And so when you look at that, the addressable register architecture, if you can do all of these complex operations, like, for instance, encryption, you can do that with my processor. So the only thing you're doing when you get a 2 gigahertz quad-core Intel i7, all you did was speed up your software, but I could do the problem set with my 816. So you can go, oh yeah, but speed is a big deal. I go, yeah, speed is a big deal, but look what it takes to get the speed there for a quad-core i7, or how many cores they have in the i7. I don't even know how many. But the point is, it's going to take a manufacturing organization like Intel has, and you're going to have to drive that down to about 20 nanometer technology to make sense out of that. And as an end result, I'd recommend you buy it. I don't have to design it. I already designed the ones I wanted back in the 80s, 30 years ago.
Yeah. So when you're designing that with your little team of 4 or 6 people, was it, you said that you did simulation in software beforehand, but then when it came to actually designing the chip, are you actually sitting down at the drafting board with Rubelith and drawing things out on plastic and paper?
Yeah, back in that day, we used Mylar because you could erase Mylar without ripping the paper. So you use plastic pens, plastic lead, and so what you did then was put the schematic. What we did, which was unique, not totally unique, I guess. I don't know if it was done by anybody else. It could have been. We drew the whole chip on one piece of paper, and it could be a big piece of paper. So when you do it that way, it becomes the layout plan for the mask design. Do you follow that?
Yes.
So if you have a data buffer here, it's on both the schematic and on the layout. If you have an address buffer across the chip, you have it right there. Now, the way that Xerox was doing it, and I taught Xerox how to design microprocessors after I started my company and after Commodore and I parted ways, my first contract after Commodore was Xerox. Xerox in Southern California, in El Segundo, and Xerox Park in Northern California, where Jobs got his GUI. Mm-hmm. So Jobs is going in Northern California at Xerox to take things. I'm going into Southern California version of Xerox, where they were doing advanced technology. I was teaching them how to design microprocessors. So I did that on the way to working with GTE and licensing GTE and Rockwell, Cinertech. I licensed all three of them on my CO2. I licensed GTE on my 816 and some of the peripheral chips like the 22 chip and other things. I've licensed over 60 companies. So what happens here is when you look at this from a semiconductor engineering standpoint, you know you have a basic building block for anything that wants to have embedded intelligence. So you're putting things into software is what takes the microprocessor hardware and I/O and memory and makes it into something that solves problems. So when I've got the world's most documented microprocessor, the world's probably most famous microprocessor, I'm saying, why would I change from that and try to build, a business out of something like Chuck Peddle did with the Commodore PET or the Commodore 64? Chuck didn't design the Commodore 64. I don't think he had much at all to do with it. But that ended up being something that someone else needs to do. I'm an empowerment technology. I want to empower people to do their idea. That's what I did for Chuck. That's why he came to me. He knew I could build a chip that would meet the requirements that he thought he could use for his systems, but then he got lost. He went to the Intel 8086 and his Cirrus computer, I think it was, and then between Bill Gates and Intel and IBM, they just knocked Chuck right out of the market because he wasn't in a position to lead. And you have to lead. And so I was leading. I have been leading for the last 37 years, the 6502 technology, because I knew what it was. Rod Orgle and I knew it. Rod says to me, Bill, if this microprocessor works as good as it will, we can go to the happy hunting ground. That means that he can die knowing he did something special with his career. Now, Rod's passed away. Others have passed away that were associated with this. And that's what we knew. We knew we had the best because 1 byte for certain instructions, 2 bytes for 0 page, 3 bytes for absolute addressing, and all I did with the 816 is add a third byte to the address, 24-bit addressing. You look at the time, 8086 had segments of, I think it could handle 4 gigabytes or something, 4 megabytes. Mm-hmm. And mine can handle 16 megabytes. So I already had a bigger linear space than Intel had. Motorola had a bigger space, but where Motorola screwed up with the 68000, instead of calling it a 32-bit processor, mm-hmm. they called it a 16-bit processor because they only had a 24-bit address bus, the same as mine. That was a mistake in marketing by Motorola. That should have always been a 32-bit processor because it has 32-bit registers. The 8086 had 16-bit registers. The 8086 was really a 16-bit processor. 68000 was always a 32-bit processor. And mine has always been an 8-bit processor with a 16-bit switch for internal 16-bit registers. So someone that knows the hardware knows that Motorola screwed up with marketing, that Intel outmarketed them. Intel always outmarketed them. Motorola went to the 8-bit or the microcontroller business. Motorola basically got out of the general purpose microprocessor business. Intel took it over. AMD is just proving that they don't have a monopoly. And there you go. So ARM came along, and ARM followed my business model. And that is you have to survive on the design, on your design expertise. That's what ARM took away that fateful day in about November of 1983. And when people say, well, what do you think about their stealing your ideas? I said, they didn't steal my ideas. I gave them my ideas. because I already went to Gold Street. Prudential Base wanted to take me public, and I had already decided I wanted to do it my way. And I don't need any stockholders. I don't need any. There's never been another member of the board of directors. It's always been, I've been the president, CEO, chairman of the board, and the board of directors. So I never get into arguments. I just don't have any negative input. And if I screw up, if we were successful, it was a team effort. If we screw up, it was my fault.
So where are you headed now with the 6502? I know you have some hobbyist-oriented boards. Is that getting traction? Tell me about that.
Okay, please. Yeah. Okay. So the Accelerator boards. Now, Accelerator, where'd we come up with that name? Accelerator uses the two X's in 65XX. But when you combine, if you call it 65 Accelerator, which we do on some of our packaging, I'm looking at it right now, we have 65XX CELER8R. What we came up with one interesting Saturday, which is unusual for anybody to work except me on a Saturday, although my guys work because they love what they do. Dave Kramer and I are talking on a Saturday, and I said, well, you know what? If you excel, that's EXCELL, and you accelerate, like in a car, ACCEL, I said, if you combine the two, you have XX, because you use XX instead of AC and EX. And then you use an 8 because we love 8 bits, and you drop out a few other letters, you get Accelerator. He said, that's the one. You don't have to think of another thing. That works. So that's where we got Accelerator. But what are we accelerating? We're accelerating the understanding and application of embedded intelligence technology. So our branding, if you look at our boards, have a big old X there for Accelerator, but what we have in the corner of the X is S for sense, P for process, C for communicate, and A for actuate. That's what embedded intelligence does. You sense your world, you process the information from the sensing of the world, you may communicate it to someone like your wife or someone else, and then you'll do something. And that's what every piece of embedded intelligence in the universe does it. So that's what we're teaching, the embedded intelligence. And so we have EIT in the middle of the X, and that's what we're trying to communicate. What we're trying to do is enable others to understand embedded intelligence is what created the universe, and it's created the matter. I'm saying something decided to matter, and going from energy to matter. So matter is created in the center of our stars all over the universe. That's the combination of gravity, electric fields, and magnetic fields. And somehow that decided to matter. And I don't know how that decided to matter or what was the trigger, except when I use my mind experiment, I'm saying I decided I was so bored about sitting around statically as energy for forever, and then I decided to wiggle along with you and others. We decided to make matter. And why did we decide to matter? We decided to matter to understand ourselves from our own senses. So this is all wrapped into the accelerator concept. And that's the philosophy of embedded intelligence that you can find on my foundation, the Mensch Foundation, which is really a short form of the Bill and Diane Mensch Foundation for embedded intelligence education. So now, these boards have the basic general purpose technology that's been used forever with microprocessors. So if you look at the 6502 on the 6502 board, I have my 21 PIA that I invented and the 22 that I invented, and then we have RAM and flash memory, so you want to change your memory for program space. Those are the basic building blocks of every microcomputer system in the world. Everything from Intel, everything from AMD, everything from MIPS, everything from Stanford and their technology of RISC, IBM, that all the same components. They just run faster. They're use up more power. They do interesting things that we love. I mean, I'm talking on a very interesting thing with, I don't know if it's quad core ARM in this Moto X or what it is, but that's what I'm talking to you. Android operating system running on ARM processors. So what I'm saying is our boards don't compete with Arduino, don't compete with Raspberry Pi, don't compete with BeagleBoard, don't compete with any other single board computer known to mankind. They're ours. They use our chips. And when we're working right now, David Gray is putting a regulator on it. So our 5-volt SXBs work at 3.3 volts. So you can connect them up to what I call a programmable breadboard, which is any FPGA board ever manufactured can hook up to our boards. So that means that if you learned how to write hardware description language, you can write hardware description language, connect it to our boards in a meaningful way, and use that experience that you learned in colleges of engineering to add to these boards in a way that a creative person would. And that leaves it open to everyone that wants to can be creative with our SXBs.
Nice. You're talking about embedded intelligence in the universe, and I thought we were going to get into a theological discussion there for a minute.
No, but we can get into philosophical discussion. By the way, I've been an advisor to Notre Dame for 20 plus years, and I just recently looked at some of their curriculum, and I noticed in their junior and senior year, an engineering student can pick either philosophy or theology. So theology is the study of religions. If someone wants to study religions, I highly recommend the book by DK. It's a publishing company out of the UK, and it's called The Religions Book, Big Ideas Simply Explained. If you want to know about philosophy, the same publisher, DK Publishing, has the Philosophy Book, Big Ideas Simply Explained. If you want to know about economics, you can buy the Economics Book, Big Ideas Simply Explained. If you want to learn about science, you can get the Science Book, Big Ideas Simply Explained. So what I'm getting at here, the theology, I'm not a theologist. If you want to put me in a category, I'm a philosophical theorist, which means that if you see a bug flying around, or a bird flying around, or a bug crawling, or a tree that has leaves on it in the summer, you got to know that they figured out how to do that. And I'm calling that embedded intelligence. So if you say, well, we only know about 50% of all the living things on planet Earth, and with all the scientists trying to figure out what the next interesting living thing is, we've only covered half of them. So what I'm saying is there's a whole lot of embedded intelligence. So if I were to, some people think I was trying to start a new religion with this idea of a philosophy of embedded intelligence. I'm saying no, a philosophy is a questioning. So when I say a philosophy of embedded intelligence, I just got a whole bunch of questions that need answers. I think we can find them. That's what our country was built on. That's why we have freedom of speech. That's why we have freedom of religion. These guys that created our country, or founders of our country, like Ben Franklin, Thomas Jefferson, George Washington, these guys, they called themselves deists. A deist believes they can know, and I add understand, God through reason and nature. Look up deism. Just see it. And it's a symbolism on the back of our dollar bill. So what I'm saying, when you say in God we trust, the only God we can trust is all of us working together, and that's my definition. You can find that online too. So what I'm saying here is I'm not a theologist. I'm saying that Joseph Campbell wrote great books on comparative mythology, and I think his writings are really helpful in understanding that the theologist is trying to understand their own religion. And I'm saying it's easier to look at all of the religions in that book, the Religions Book. Just read that. You can see every religion that they could figure out when they published it, and it's built by a whole bunch of people that are really uneducated, and they're listed in the front of the book. So I'm saying in 2 or 3 pages, you can figure out what Christianity is about. You can figure out what Judaism is about. You can figure out what Buddhism is about, which is actually a philosophy. You can figure out what Hinduism. There's some magical religions, and I think they're all good. I think there's some magical mythologies, and everybody that's anybody from indigenous further all have their mythology. A mythology is the answer to questions unknown. Scientists try to figure how things out, and that's where Galileo ran into trouble with the Catholics. And the point is that a scientist is looking for answers to the philosopher's question. I'm trying to understand how to apply that. So as a result, these boards are supposed to be a foundation for understanding of embedded intelligence in all of its forms. If you get online and look at the little slideshow that Dave Kramer helped me with 4 years ago, you can see I'm comparing natural to man-made. The top of the slide is natural. The bottom of the slide is man-made. My microprocessor was used in all the bottoms, like pacemakers and all these other things. So look at the complications of replacing a natural pacemaker cell that every one of our hearts have to start with, and replace it with something we build because the natural cell stopped working right. It's very complicated. And St. Jude's is one of the licensees that used my microprocessor, and they acquired 3 or 4 of my licensees. One of them was Siemens Pacemat. So I'm saying I understand that my embedded intelligence technology in the microprocessor form can enable and empower other creativity that hopefully is beneficial for mankind.
Awesome. What haven't I asked you that I should have?
How old am I?
How old are you?
70. No, I was just kidding about that.
Are you going to keep going? Well, okay, you're 70 years old. Are you going to keep doing what you're doing for the time you have left on the planet?
Yeah, my goal is to live to be 100. I want to beat my aunt, who was my father's sister, my father's only sister. My father didn't have any brothers either. So she lived to be 100 plus about 2 or 3 months. So I'm going to try to beat her. So that means I have about 30 more years of doing things and that I love doing. But really, I retired when I was 33. And what I call retirement is doing what you want to do. And that's what I've been doing. And if I didn't do it, then you got to ask yourself, why didn't you do what you wanted to do?
Right.
So if that's one definition of retirement. So I'm never planning on retiring from this technology. And I'm never planning to have this technology not available in some form. Now, you got to know that with our programmable logic boards, you got PMCUs. I think we're the only ones that are supplying PMCUs. However, others are. They just don't call them that. A programmable microcomputer unit. Now, my definition of microcomputer is a microprocessor, I/O, and memory for data, and memory for program. So when you build a microcontroller like an Arduino, you're outfitting a microcomputer with some special circuitry to interface with maybe some analog signals like sensors and some digital signals. So we don't really think of ourselves as doing that. We think that the analog stuff should be put on it. So we will have shared projects with Mauser's Project Share website where we say, okay, here's an A to D converter you can hook up to the memory bus of our parts, or hook it up to the 22 and exercise the data bus with one port and the control bus with the other port. And that's what people have been doing for 35 years, maybe longer. So what I'm getting at is when you look at it as being in a hardware description form of it, my foundation can make that technology available forever. That's what my plan is. So I already have the PMCUs. I already have the programmable boards. PMCUs can be loaded into any fabricator of programmable logic devices like FPGAs. So any board can use that PMCU. So you could say that for all eternity, the 6502 and 816 in programmable microcomputers will always be available to mankind. Now, with that in mind, you can go, if we ran the 816 as an example, on the most advanced processes that ARM is, or Intel is running their processors on, we think we could run at 10 gigahertz because we only need 8 bits of data. And everything is running on the chip, so we don't need any cache. So you can have the full memory space of the 816 in what would be considered all cache. So what we're saying then is if one was inclined to do it, we can run as fast or faster than any ARM processor or any Intel processor, and we will always be able to do that because the manufacturers, whether it's Intel or Global Foundries that acquired all of IBM's semiconductor operations, silicon on sapphire, or silicon on insulator, would be an example of something that runs faster than anything Intel has or ARM's running on. We could do that with ours because we have a simple processor that just gets the job done. So if you just take your calculator and look at 10 gigahertz running of the this opcode, what could you do, or what couldn't you do with that? That's the question. What couldn't you do? And see, one of the things that's important is to recognize that Microsoft, working with IBM and Intel, really defined a platform for software engineers to work on. That's why I use Windows. It's 10 times as many systems out there than what Apple has as far as Macintosh. Macintosh is a wonderful system. Now, you'd think that I was a big fan of Apple, and I'm not. The reason why I'm not is they killed off the Apple II to make room for the Macintosh. Mm-hmm. And a lot of disappointed people followed that. Mm-hmm. And they could still be selling a product with the Apple II technology and the 16-bit processor. They could be doing that better than ever, and they chose not to because they wanted to make more money on the 68,000, which became the PowerPC, became the x86 from Intel. Mm-hmm. Now, there's another example. If you need an example of why I didn't do the 32-bit, just look at Motorola, IBM, and Apple doing the PowerPC. And at the end of the day, after all those billions of dollars invested, after all of those thousands and thousands or millions of hours by designers, Apple chose Intel x86. So actually, the PowerPC was a prototyping platform for the Intel processor. That's the why I never did the 32-bit. So if you want to use the PowerPC or MIPS processor or Spark processor after, what's his name bought it, I'm saying you've got some examples of what could have been but never would have been because of the marketing and the capital pressures of big business.
I think this will be my last question. You mentioned using the 6500 hardware forever. So people who listen to this podcast are still using their Atari computers with their 6502s, and if you could send them a message, and you can right now, right, what would you tell them?
Right. Well, I tell them thanks for the joy of working with this technology. It was designed with a lot of love, a lot of care, a lot of heart, and I think it continues on with the people that want to use it. And so I would say that, unfortunately, Atari being acquired by Jack, and I don't know what Atari is doing anymore. Commodore that went away was another thing that Jack got involved with. And, the Commodore, I saw a Commodore smartphone recently with a Commodore, I don't know what it's called, on it, but just like an Apple logo on the back of a smartphone. Yeah. So the brand name has some value to it. But the real problem is that most of those people don't have the, I don't know what you want to call it, the camaraderie thing, the love that's needed to I don't know, support the market interest. But the Atari, I think, could come back as probably, whether you know it or not, the 816 was designed because the CO2 has an extra cycle in decimal correct, which the asteroids broke up, and So Atari never used the CO2, but they could have used the 816 because I found another way of doing decimal correct with the same timing. So the timing of the 816 would allow the asteroids to not break up at the 1 megahertz clock rate. So actually, if you took the 816 and built a new Atari out of it with something that would be interesting, and you look at the cost of that, see, so most people want to compete with, let's say, the Arduino $2 value, which is a not-for-profit company giving away things, but they have to assign a purchase price to it, or the person getting it might just look at it and say, that's nice, and put it in in their drawer and never use it. So what I'm getting at here is for those Atari folks, I would love to work with somebody that really had the brand and really wanted to come out with a 16-bit Atari that would do some fun things. But it has to be done with state-of-the-art technology. You could build a brand new Atari with if someone had the brand, you could build a brand new Atari with the fun legacy stuff that is what people like playing around with or doing things with. And if you did that, I think you would have a following because there is a love for the technology. There's as much love for the Atari brand as there is for the 6502 brand, in my estimation. So I cheer for Atari. I know Nolan Bushnell. He's the one that gave me the award on the 25th anniversary of microprocessor. I got the first award. Chuck Peddle got the second award, and then the other 7 awards were given. Other 5 awards were given out, I guess, for the other 5 processors. But Nolan Bushnell is very creative. Was very creative, and when in 1996, when that award was given me, I talked to Nolan what he was interested, and what he was interested in, what he's working on at the time, was multiplayer games. And I thought, multiplayer games? What? One game at a time is enough, or one player at a time? But that's what we're doing now all over the world. We have multiplayer games. So Nolan Bushnell knew what he was doing in 1996. But see, I think it takes somebody that just has a vision and a dream, and bringing Atari back to life with the 16-bit 816 is what I would enjoy helping them do. But that comes from the love of the technology, not from somebody wanting to make the next $1 billion.
Right. I wonder if this is what you're talking about. This cartridge is called Project Veronica, and this cartridge has a 65C816S CPU clocked at 5 megahertz and 64K of RAM. And this plugs into the Atari 800, one of the Atari 8-bit machines, and lets you run 816 software on it.
Yeah, so then you have to, right, that Veronica, I've heard of that. I forget, a woman designed it, right?
I don't know. I don't.
Yeah,
I was going to tell you what country it came from, and it's somewhere in Europe, I think. I'm not sure.
Yeah, see, that to me, again, this is about Atari. You asked me the question, and I'm saying I have an Alfa Romeo Spider that's 26 years old. Uh-huh. When I was a kid, I got a 29 Model A, a 1929 Model A, and it was about 1962 when I was in high school. I got that back on the road, and that's wonderful. But I never thought of dropping in a 409 engine into it. I didn't think I was going to do that, and I didn't want a kit car which would look like like a Ferrari. I didn't want a kit car that had a Volkswagen engine in it. I like the real thing. And so when you add in a new engine into an old Atari system, that's what I would call a hobby market. Mm-hmm. What I'm talking about is a real market. And that is if you took the Veronica and said, what would be an attractive case that would have the Atari brand on it, and that was actually sold by Atari. And I'm saying that is possible, but you have to acquire the brand. Maybe somebody can work out and negotiate rights to use the Atari name and do a real Atari game with the 816 in it, and you take that card. What's the difference between that card and the whole freaking Atari? I'm saying the only difference is a display interface and a keyboard.
Mm-hmm.
And I'm saying, just do it. You could, and I don't think having a cigarette case or whatever you call it, a little, what do they call those? Mints come in, or a chewing gum comes in.
Altoid.
Yeah, an Altoid box with, you plug in a keyboard and plug in a display, an HDMI display into an Altoid keyboard. I mean, what does that feel like? I mean, there's a feeling about the product. This is what Jobs did so well. So you have the feeling for it. So in other words, you could take, a 3D printed case that has it's what automobile companies do all the time. If you buy an Audi, you got a certain shape. If you buy a Ford, you got a certain shape. You got a certain grill. The grill looks and General Motors has theirs, and they morph those. Volkswagen did that with their new Volkswagen. If you take the idea and take the industrial design of the old Atari and hook to that, then an HDMI display or whatever you want to do to drive your HDMI TV, you just take that box, make it look like an Atari, but have the 816 in it running at, you can run that comfortably at 8 megahertz, but with our hardware description, you can run it at whatever megahertz you want. And so what I'm saying is taking the Atari brand name and have the IP, knowing that you pay whoever owns the Atari brand, you split your whatever, you split your you give them a royalty on the name. Then you have a real Atari. Then you say that's an Atari. But right now, what people are doing is saying, well, I can emulate it on my Android phone. I can play all my Atari games on my Android phone with a JavaScript emulator. You can run it on your 2 gigahertz Dell computer and tablet or whatever you want. You can do all that. That isn't the same, my friend. And that's what I'd recommend to the Atari fan base. They find a way to bring it back to life. And then all of those boxes that you're still playing with has a future. And you can look at that future and say, but I have Model A. I drive my Model A. But that's what I'm saying. All of those old brands, Apple II, Commodore, Atari, and the old Nintendo, could all come back to life with the right relationship. And we have the technology. And of course, I'm selling an idea that benefits not only my company and my employees, but I'm also suggesting it for anybody that's in love with what they're talking about. And there's a lot of love for Atari.
Nice.
You're welcome.
Thank you, Bill.
Thank you. Thank you for inviting me to talk with you today, Kevin. By the way, just in case you want to do it, if you want to have another one of these, I'm open to as many as you can stand.
Great. Thank you. What will happen is here's what will undoubtedly happen. I will post this in a month, and then I will get 10 or 20 emails from people going, why didn't you ask them about this or that or the other thing? And then I'll make a list, and then we'll maybe have another conversation.
That works for me, Kevin. You hate to have an unanswered question, don't you?
Yes, I do. Thank you, Bill. I appreciate your time.
You're welcome. Thank you, Kevin.
If you enjoy these interviews and would like to contribute something, I encourage you instead to donate to one of our favorite organizations, the Internet Archive, at archive.org. The Internet Archive is a nonprofit digital library with the stated mission of universal access to all knowledge. They've done incredible things to preserve computer history, including hosting thousands of programs in an in-browser Atari emulator, creating the Wayback Machine, and offering full-page scans of countless Atari computer books and magazines. Make your tax-deductible contribution at archive.org/donate.